All right, today we are going to talk about the concept of spontaneity. So, in chemistry, spontaneous doesn't necessarily mean like suddenly. It doesn't mean to be unplanned, like a person who might be spontaneous. They just spontaneously decided to go take a trip or buy something. Spontaneous in chemistry means that it happens without continuous outside help. So, for example, when you strike a match, you are giving it outside help. You're rubbing the little match head across some sandpaper, and that friction is helping it get started. But that's not the same thing as continuous outside help. You don't have to keep striking the match to keep the thing burning. So that is considered a spontaneous process because it doesn't require a lot of help from the outside. Just a little spark to get it going. So a spontaneous process does not necessarily mean that it happens quickly. So if you take rusting of iron, for example, where you combine iron with oxygen to get iron 3 oxide, that is a spontaneous process. If an old car sits in a junkyard for 30 years, it's going to get pretty rusty, all pretty much by itself. Like, obviously it's getting wet and there's oxygen involved, but you don't have to constantly keep pushing the reaction along. It happens spontaneously. It happens on its own. Okay? So if a sample of iron can rust without much help, this is spontaneous, even though it might take months or years to complete. Now, an example of maybe the opposite would be, if you're baking cookies, right? You put the cookies in the oven, it causes them to rise, but that rising depends on continuing to put in that energy from the oven. If you are supposed to bake them for 10 minutes and you take them out after 5, they're not going to finish rising because the chemical reactions that are causing that increase in volume of the cookie are non-spontaneous. It needs continuous outside help. So that cookie rising would be an example of a non-spontaneous process. Now, when we talk about trying to predict if a process is going to be spontaneous or not, there are 2 main factors that go into it. The first has to do with heat. Most spontaneous reactions are going to probably do what with heat? Like, what's the most common type, endothermic or exothermic? Well, the most common thing is for a reaction to give off heat. So exothermic is way more common for a spontaneous reaction. The other thing, though, is most spontaneous reactions are processes, regardless of whether they give off heat or they absorb heat. They do something with their organization, their level of organization. Most spontaneous reactions or processes increase entropy. So that's a new term for us. But entropy basically, it's complex and there's a physics explanation to it. But for our intents and purposes, we can think of entropy as being randomness. In other words, disorder. So it's the randomness or disorder of a system. And if you think about, just experiences from your own life, do things tend to become more organized or less organized, assuming we let them go and don't continuously put in work? Like, does your bedroom at home just sort of naturally become more random and disorganized? Or does it just, do things tend to fall into a nice ordered, organized state? I think most people would agree that things tend to become more disordered over time on their own. Again, if we are not intentionally putting in energy to organize them. All right, so let's talk about predicting entropy increases. Entropy is going to increase in a couple of different ways. One way would be anytime a solid or liquid dissolves. So if we think about what's happening when we dissolve something, if we have a cup of water and we start off with some nice organized crystals of sugar and we drop them into the water, and now they become very spread out and just sort of randomly distributed throughout that water. Well, that's more disordered, right? That's the natural sort of direction that something will go when it dissolves. Also, anytime you add energy to something that causes a change in state, so like melting a solid or boiling a gas, those are going to, boiling a liquid into a gas, that's going to result in an increase in entropy, all right? And then anytime a reaction occurs which increases the number of moles, that is going to cause an increase in entropy and randomness. So for example, when we look down here at NH3 decomposing into N2 and 3 H2s, we have 2 moles on the left and we have a total of 4 moles on the right. So we're kind of ungrouping those atoms. We have them a little bit more organized back when we only had 2 moles over here, and now they're a little bit more spread out when we have 4 moles over here, right? Sort of like when the bell rings and everybody leaves class, we go from having, 60 or 70 classes going on to having 1,000 individual students in the hallways. We are ungrouping our classes into individual students, thereby increasing the randomness. Okay, calculating delta S is pretty straightforward. It's just like calculating delta H. And I should have said this earlier, but S stands for entropy. It's the symbol that we use, right? Is a capital S. So when we say delta S, we mean change in entropy, right? And so to do this, we have to look at numbers on the table, and I'm talking about the table of thermal properties that I gave you back when we learned about heat of formation. So I'm talking about this table right here, okay? So if we look at this last column that we haven't used yet, where it says S, each of these substances has a different value for entropy. Okay, so you can see aluminum is 0.028 kilojoules per mole times kelvins. We'll talk about those units later. Aluminum sulfate is much higher at 0.239, but they all have their own values. Okay, so if I want to calculate delta S, or change in entropy, I have to do the S of the products minus the S of the reactants. And so I'm going to do this the same way that I did delta H, so products first minus reactants. So for example, if I look up N2 as my first product on the table, I can see N2 has an entropy of 0.192. So delta S for this reaction, I'm going to start with my nitrogen, 0.192, and that's kilojoules per Kelvin. It's technically kilojoules per mole times kelvins, but we're dealing with just 1 mole, so we've kind of already taken that into account. My other product I have 3 of, so just like heat of formation, I'm going to multiply it by 3, but that is my hydrogen, H2, which, if I can find it here, oh, here it is, 0.131. Okay, so 0.131 kilojoules per Kelvin, and then those are my 2 products, right? So I just took care of those two substances, and I'm going to do products minus reactants. So my only reactant is this 2 moles of NH3. So I find it on the table. So NH3 is right here, and it's 0.110, but I do have to multiply that by 2. And then we simply calculate. All right, and this gave me 0.365 kilojoules per Kelvin, and that would be my entropy. Now, we can't really say endothermic or exothermic when it comes to entropy. It can be positive or negative, right? And so since this number is positive, again, I'm just going to say it's an increase in entropy. All right, so for this reaction, entropy is increasing. All right, so that brings us to determining spontaneity. So we said that if something is spontaneous, it typically will have a negative delta H, and it will have a positive delta S, meaning a loss in enthalpy but a gain in entropy. We can actually put those terms together and find out once and for all if a reaction is going to be spontaneous using this equation called Gibbs free energy. So free energy is just the energy available to do work, okay? And we will do it by taking delta H minus temperature times delta S, and if we get a negative answer, then we have a spontaneous process. So let's take a look at an example. It says combustion of CH4, and it does give us a temperature of 298 kelvins. So the first thing we need to do is calculate the delta H. We've done this one before, so I'll just do this one real quickly. Well, actually, the first thing we need is a balanced equation, so we'll start off with that. Okay, now this one is going to give us CO2 and H2O. Remember, H2O is a gas. Go ahead and see if you can calculate delta H using your heat of formation for this reaction. Okay, so there's my delta H. It looks like negative 781.3, so we can tell this is a very exothermic reaction. So far, I would expect this to probably be spontaneous because most spontaneous reactions are negative delta H's. But next we need to find our delta S. So again, using that thermal properties table, we're going to use the S column this time and see if we can find the delta S for this reaction. All right, and I got a value of negative 0.004 kilojoules per Kelvin. So this actually represents a decrease in entropy, which is sort of unusual for a spontaneous reaction. So we'll see if it is in fact spontaneous. Hopefully you see where I got all my numbers. I'm just looking on our thermal properties table. I'm starting with my products like CO2, so its entropy would be right there, 0.214. Then I have my other product, 2 moles of H2O, so there's that. Remember, since it's combustion, H2O would be a gas. And then on the reactant side, I have CH4, so there's its S value. And then last but not least, I have my 2 oxygens, so there they are. And elements do have S values. They don't have heats of formation, they're always 0, but they do have entropies. Okay, so the last step is to use our equation that we just learned, so that's this one up here, delta G, and we're going to plug in our values. So let's get this started. So delta G equals delta H, which is negative 781.3 kilojoules, minus T, which stands for temperature. And in this case, we are at 298 kelvins, times delta S, which is negative 0.004 kilojoules per